What is the difference? Classical theory says that energy of these resonators are continuous. So they take whatever, how much energy is given to them. They have no choices. But in here, we also said that these resonators only absorb energy at some discrete amounts and give off at some discrete amounts.
So the amount they absorb is limited?
Limited, yes, you are right, that's the point. Limited. Or limited is, yeah, maybe we can say this word as well. Limited is also possible. So then, on this basic, Max Planck wrote some postulates, yeah, some consequences. In modern physics, those things are called postulates, yani statements, some statements. Now, we are going to learn those statements, what Max Planck said. The total energy of a resonator is an integral number of HF. Integral number means 1, 2, 3, 4, 5, 6, 7, and so on. Yani 1 HF, 2 HF, 3 HF, 4 HF, and so on. That's why the real equation has energy of a resonator can be n times HF. What is H? H is Planck constant. Because this is Planck's theory. Planck's constant. How much is this number? 6.63 times 10 to the power negative 34 joule times second. This is the universal constant. Just like universal law of gravity, we have capital G. It was 6.62 7 times 10 to the power negative 11. It was the same everywhere in the universe, universal. This is another universal constant. Yeah, Planck's constant. This is Planck constant. H. What is F? Frequency of the resonator. At what frequency the resonator vibrates. So HF is the, and if you multiply this HF by 1, 2, 3, 4, 5, you can say that a resonator can have only this energy, not between them. Discrete, not continuous. F is the frequency of the resonator, and is the integer called quantum number. This n is called quantum number, 1, 2, 3, 4, 5, and so on. Quantum number. Second postulate, what he said is, because total energy of resonator comes in discrete units, not continuous, it is said that energy is quantized. What does quantized mean? I explained you when I was talking about some older courses. Electrical charge is also quantized. 1 electron, 2 electron, 3 electron, 4 electron, but not 1.1, not 1.2, from 1 to 2, because you cannot divide electron. So quantized means this. Energy is also quantized. This is revolution. Until that time, nobody think this way. Continuous. But now quantized, discrete. So it is said that energy is quantized. With this idea, a new theory is born, which is called quantum mechanics. The beginning of the quantum mechanics started with Max Planck. Quantum physics. Start with it. And every resonator can vibrate at some discrete energy. Some energies which allowed energy levels are called quantum states. And remember, we said that a resonator can vibrate at HF, 2HF, 3HF, 4HF, and so on. All these energies are called quantum states. First quantum state, energy is H times M. Second quantum state, 2HF. Third quantum state, 3HF, and so on. Later, Niels Bohr will say these quantum states as energy levels. Chapter section 2, we will talk about energy levels of the atoms. And every model from then on developed is based on this model of the Planck's. Albert Einstein used this model, Niels Bohr used this model, later coming all the scientists used this model. So allowed energy levels at what energy a resonator can vibrate called quantum states, HF, first quantum state, 2HF, second quantum state, third HF, third quantum state, and so on. Later it will be said as energy levels, we will study section 2. Third one, if a resonator remains, this is another revolutionary thing. If a resonator remains in one quantum state, no energy is emitted or absorbed. For example, say that a resonator vibrates at a quantum state which is h times f. It doesn't emit a radiation. But how will it emit radiation? Jumping. Now formula. By jumping from one quantum state to another. A resonator absorbs energy. Yani it takes energy, then jumps from first quantum state to second quantum state. Then turns back again. As it is turning back from second to first, gives energy. Yani önce jumping to second floor, going to the second floor, then jumping down. As the jumping down gives this energy, decreased energy, and in the form of electromagnetic radiation. So by jumping from one quantum state to another, a resonator absorbs, then gives off this energy in discrete units of the light energy, HF. From second to first, 1 HF. From 3 to 2, again 1 HF. This given energy is called by Max Planck quanta. Quanta. Later, Albert Einstein will say this quanta photon. But first, what he said is quanta.
That quanta is from, for example, 1 HF.
Yes, HF. Quanta. 2 HF, 2 quanta. According to Max Planck's model. 3 HF, 3 quanta. And fifth one, if quantum number changes by 1 unit, means 4 to 3, changes 1 unit, 3 to 2, 1 unit, 2 to 1, 1 unit. The amount of energy, of course, as it is quantum number decreases, energy must be given out. So the amount of energy radiated is calculated in joules by the equation of h times f. Remember, I said that 1 quanta is equal to 1 hf. So 1 jump from 3 to 2, 1 jump hf. 2 to 1, 1 jump hf again. From 3 to 1 if it is jumping, 3 to 1, how many hf? 2 hf. So h and f is the equation for calculating energy of 1 quanta. H is again, we know, Planck's constant, but f is frequency of the resonation, and also at the same time, what frequency of the emitted light, emitted radiation. What is f equal to? We know that in chapter 3, v is equal to lambda times f. In here, v changes to c because speed of light is spatial, because speed of light is a constant number, it doesn't change. So instead of v, we are going to write c, speed of light. Lambda times f, I think everybody must know that. They will give, or don't give, I didn't check the question, I forgot 2 for 2 years. But c must be known. Yeah, speed of light, everybody must know. 3 times 10 to the power 8 meter per second. C is equal to 3 times 10 to the power 8 meter per second. When you see here, you are going to write that number. C is equal to lambda times f. If instead of f, you would like to write its equivalent, so f is equal to c divided by lambda. Sometimes this equation will be written in terms of lambda. E is equal to h c divided by lambda. H c divided by lambda. Instead of f being inserted, it's equivalent c divided by lambda. And result will be calculated in joule because energy. It's energy, unit of energy is assigned to it. Joule.
So energy is inversely proportional to wavelength.
Yes, correct. As wavelength gets longer, energy of the quanta decreases. But joule is a very big energy when you are dealing with small particles, small quanta. Quantum is so small. Generally, energy of quanta is expressed in terms of electron volt. What is electron volt? Now let's define that. Energy for atom is often expressed in electron volt, EV, electron volt. Definition of the electron volt is a mystery exam question. An electron volt is defined as the energy that an electron and proton gains when it is accelerated through a potential difference of 1 volt. You know what potential difference means? I explained before. So say that there are 2 points, A and B, and you connected a voltmeter between these 2 points, and you measure that potential difference between these 2 points is 1 volt. Then you put an electron in here, And this electron starts moving, accelerating from this point to that point. It accelerates. Of course, when it's accelerating, it will gain energy. How much energy is gained from point A to B is called 1 electron volt. Because charge of electron is E. Multiplied by 1V, result becomes 1 eV. Yeah, 1 eV. This is the definition. If proton is released, you know proton electron moves in opposite direction. You should release proton from this point. It will accelerate to that point. Again, it will gain 1 eV energy when it accelerates from here to there. Definition. An electron volt is defined as the energy that an electron or proton gains when it is accelerated through the potential difference of 1 volt. 1 electron volt is energy. But we know charge of an electron, how many coulomb or proton? Yeah, equal 1.6 times 10 to the power negative 19. Right instead of E, 1.6 times 10 to the power negative 19 coulomb multiplied by 1. Result is what? It's the same number. Only you are changing EV to Joule by this way. Yani 1 electron volt is equal to 1.6 times 10 to the power negative 19 Joule, because the sign of it is for energy is Joule. We don't use in calculation of electron volts. Joule must be first converted, then you should go that way. And I think this is a ministry exam question. Also, this is a ministry exam
When you
question.
get the answer in Joule, you're going to divide it by...
Well, yeah, by 1, and then you can get electron volt as well.
Teacher, the electron volt is only the energy of the electron.
No. Electron volt is just definition. Yani energy of an electron. But şimdi, if I say I ate some food, I got 100 joule energy. So someone else also can eat and get 100 joule energy. Joule is not belongs to me, for everyone.
Yeah.
Similar in here.
Okay.
It's just a unit. How we express how big or how small energy is. Okay, no problems. At the peak of the sun radiation spectrum, each photon carries an energy. Now it says photon. Normally, Max Planck didn't say the photon. He said quanta. Albert Einstein said it. But in the question they said, they are the common text. Each photon carries an energy of 2.7 electron volt. Energy is given in electron volts. What is the frequency of this light? So I think it's not that hard, huh? Energy is equal to H times F, because 1 quanta, 1 HF. 2 quantas, 2 HF. But it's just 1 photon, 1 quanta, 1 HF. A is equal to 1 HF. Correct? 1 photon, 1 quanta. So F is the question. How can I calculate it? So divided by H. F is equal to E divided by H. E is given as how much? 2.7 electron volt. What electron volt?
We have to
Must be converted to joule. We know how to convert it. 2.7 electron volts multiplied by 1.6 times 10 to the power of
Negative 9.
yes. As you see, it's not that new, huh? Divided by H. How much is H? It's given 6.63 times 10 to the power of negative 34. Only in bracket, use bracket for denominator because there's an exponential number. And the result is going to be how much?
6.5 times 10 to the power of 14.
6.5 times 10 to the power of 14 hertz. This is the frequency of this radiation, of this light. Practice problem, next one. Assume that a pendulum, the pendulum of a grandfather's clock, old-fashioned clocks, pendulums, remember, acts as one of the Planck's resonators. They're vibrating. If it carries away an energy of 8.1 times 10 to the power negative 15 electron volt, again energy is given. In one quantum change is H. Yes. One quantum change is equal to H times F. Yani E is equal to HF. What is the frequency of this pendulum? Calculate F. Calculate F.
10 is equal to.
Yeah, same thing. Same thing. I give this question only to explain that, because what does one quantum change mean? One quantum change corresponds to HF. Two quantum changes, 2 HF. If it says 3 quantum changes, 3 HF, and so on. The rest, you are going to use equation. F is equal to E divided by H. E is given as 8.1 times 10 to the power of negative 15 electron volt, but of course we should convert it to joule. 1.6 times 10 to the power of negative 19 divided by H. How much is it? 6.63 times 10 to the power of negative 34. Result is 2 hertz, I think. So this pendulums of the clock vibrates with 2 hertz frequency. One more problem we will solve, and then we will finish this title. Radiation emitted from human skin reaches its peak at lambda 940 millimeter. So this is wavelength of the radiation. As you see, it's long wavelength compared to the other radiations. So these longer wavelength radiations are emitted by human bodies called infrared. So all hot objects emit invisible radiation called infrared, and our body also emits infrared. In part B, they are asking you what type of electromagnetic waves are these. Electromagnetic waves emitted by human body is infrared radiation. This is infrared. So wavelength is given, lambda 940 millimeter. What is the frequency of this radiation? Again, but this time we are going to use the energy equation in terms of lambda, not frequency. Pardon, first get frequency, sorry. First get frequency. C is equal to lambda times F. So F is the question. So F is equal to C divided by lambda. C is speed of light. Most probably they will give in the question, but no speed of light. Speed of light is one of the most important constants in the universe. So 3 times 10 to the power of 8 meter per second divided by wavelength is given 940 millimeter, but we should convert millimeter to meter by multiplying 10 to the power of negative 3. In solution part of in the multiplier there is a mistake, so just go this way. 3.2 times 10 to the power of 8, I think. 8 hertz is the frequency of this radiation. And how much energy? Now this time energy will be calculated in electron volts. At first you should calculate it, of course, in joule, then we should convert it. Carried by one quantum, again one quantum. One quantum is H times F. Yani E is equal to HF. E is equal to H times F. 6.63 times 10 to the power of negative 34 is H. F is we calculated 3.2 times 10 to the power of 8. So how much is the answer? So again, you calculate it. Say
2.1 times 10 to the power of
negative 25 joule. But answer must be given in terms of electron volt. Question tells you that. So this energy electron volt is equal to energy in joule divided by 1.6 times 10 to the power of negative 19. So 2.1 times 10 to the power of negative 25 divided by 1.6 times 10 to the power of negative 19. How much is the answer?
It's 1.33 times 10 to the power of negative 6.
Negative 6?
Yes.
Is it that big? That small?
Yes.
Alright.
I rounded. It was 32.
It's okay. So this is all about the Planck's model. Tomorrow we will continue with the photoelectric effect. And most probably we will finish this section tomorrow.
Thank you.